on the desktop for you to see clearly. It's hard for me to tell based on my screen, but I have all my desk lamps on today, so. Yes, maybe?
That looks fine.
Looks work, okay. So chapter 4 is cyclic alkanes. And the thing you need to know about cyclic alkanes is there's reduced freedom of rotation about your sigma bonds. You can never rotate around a pi bond without breaking it, right? You can't rotate around this carbon-carbon bond without breaking this carbon-carbon bond, because everything's kind of held together. And that introduces new strain. So the thing you really need to be focusing on as you go through the chapter 4 videos is the additional strain that's introduced by constraining also another type of strain that's related to the bond angles, because if you have a small ring like cyclopropane, right, that bond angle is 60 degrees. It's an equilateral triangle, so there's no way that that bond angle can ever be anything other than 60 degrees, but it's an sp3 hybridized carbon, right, because it's tetrahedral. Molecular geometry, well, it's tetrahedral electronic geometry. But it can't be tetrahedral molecular geometry because it's a three-membered ring, right? It has to be a 60-degree angle there, not a 109.5-degree angle. So that's a problem. That means that the orbitals can't actually overlap between the two nuclei. So if you're looking at your carbons, right, there's your bond angles. Your bond angles are 60 degrees, but your orbitals aren't there. Your orbital's actually out here. Right? The angle between these two orbitals, and I may be exaggerating a little bit, the angle between these two orbitals is 109.5 degrees. Right? The angle here is 60 degrees. That's a mismatch. What that means is that your electrons are out here. They're not between the two carbons, which means the carbon nuclei are seeing each other. And if the carbon nuclei are seeing each other, they're repelling each other. And that's going to introduce some strain, and it causes the cyclopropane ring to be significantly less stable. Why do you care if there are additional sources of chemical behavior of the molecules? So you want to be focusing on identifying the types of strain. That's what the quiz on Tuesday is going to ask you to do. It's going to ask you to look at cyclic structures and find the torsional strains and find the various steric strains within the molecule, and then talk about why that strain can't be relieved if there's not free rotation about some bonds, for example. So we say this orbital is really pi-like because the electrons are in the same place that they would be for a pi bond, right? If you have a carbon-carbon, they're not doing as good a job holding those nuclei together if they're out here as they would be if they were right in the middle, right? So there's a pi bond versus the sigma bond, which would be the two orbitals overlapping, right in the center. That's the one that's cylindrically symmetrical around the bond axis. So the sigma bond is stronger than the pi bond. An average carbon-carbon sigma bond is somewhere around 85 per mole. And as it turns out, this bond is also about 65 kilocalories per mole. Which shouldn't be that surprising, because the electrons are in the same place relative to the two carbon nuclei. That's electronic in nature, because it's dependent on kind of where the electrons are and how they're holding things together, rather than electron clouds either passing close to each other or passing through each other. So you should be on the lookout for that. That strain decreases as ring size increases. By the time you get to a cyclohexane, right, it's a regular hexagon, those angles should be 120. Well, 120 is a lot less far from 109.5 than 60 is. And you get more flexibility. The larger the ring gets, the more likely it is to take a conformation that's not planar. In fact, cyclohexane isn't planar. We actually have bond angles of 109.5 in that chair, and it releases the eclipsing. the hydrogens are no longer overlapping. So these two hydrogens, right? These two hydrogens now are 60-degree dihedral angle. It's staggered. And you can, right, so I've got this carbon here coming up, and then this carbon there kind of going back, and then I can fill up the rest of the, right. So these hydrogens that I've drawn here, you'll notice that's completely staggered. Everything's a 60-degree dihedral angle. So it's strain free. There's no bond angle strain, because when I go into that chair conformation, I make the bond angle 109.5, which is the same as the orbital angle, and I also, in the axial positions, can interfere when the substituent is not hydrogen. And that's a new type of strain called a 1,3 diaxial strain. Right, if I were to number the ring, carbon 3 there, so that's a 1,3 diaxial strain. When they're hydrogens, that's not a big deal. But if these were methyl groups, they'd be overlapping van der Waals radii, and so they'd be interfering with each other. That's a new type of strain that you don't have except when you have a cyclopentane or a cyclohexane ring. There's another type of strain that you introduce when you have even numbered rings, like cyclohexane. Right? These hydrogens are actually, even with hydrogens, they're pointing at each other and they're overlapping. That's called a transannular strain. Annulation is ring formation, so when you say transannular strain, that means from across the ring. So in positions 1 and 4, in the boat form of cyclohexane, we have that transannular strain. And you'll have that in any even numbered rings. The molecule will have higher energy and therefore be likely to react in certain ways that it can react in order to reduce the amount of energy. So I think that's really all I want to do there.